Sorry we had to miss last week. Actually, got back in town right around 5 o'clock, so we could have had class for an hour and a half, but we had no way of telling that. We had a fantastic bus driver. He passed every other bus that left in front of us. I mean, he was driving safely, but he was steady at it. So that's why we got back as rapidly as did. If we'd have had some of the others, we probably wouldn't have made it back as soon. Now, can't think of any major announcements that you might need to know. The question was raised about how many more meetings we have. We have tonight, and we have next Wednesday night. That gets us to the 24th, and the next Wednesday after that is May 1st, which is in finals week. So what I'll do is next Wednesday night have your last test, which will probably be the Chapter 17 test. I don't think we're going to get into 18. If we do, there may only be one question on it or something like that from Chapter 18. But we'll see. If we get that far, I'll adjust that. But right now, I'm anticipating just the Chapter 17 test next Wednesday. And you'll have 1 week to do it. I'll be back here on the Birmingham East Campus the following Wednesday. That's May 1st, and I believe that, yeah, that's right. And so I'll be here from 4:30 to 6:30 again. So if you want to, you can bring your test then. If you happen to be on the Bessemer campus anytime beforehand, or Friday morning on this campus, I'll be over on the Birmingham East Campus, West Campus. And do y'all know where Dr. Pruitt's office is? No. Do you know anything about that campus? Huh?
What, science building?
Yeah, the science building is a little building in between the library and the academic building.
Right.
Okay. The academic building, which is the back part of that that quad, you might say, the last room before you go down the half flight of stairs to go out to the baseball field, the gym, that kind of thing, right at the top of those stairs is Dr. Pruitt's office. It's room 1B122, I believe it is. Yeah, 122. And that's where I am on Friday mornings from 8 to 12. So I'm usually there before 8. I'm usually there after 12, but definitely there between 8 and 12. Now, they love calling meetings on Friday, but hopefully, being right before finals, they're not going to call any meetings. So hopefully I will be there from 8 to 12 that Friday. Okay, so if you don't want to have to come the next Wednesday night, if this is inconvenient, you can bring it that Friday. Or if you live or work out near Bessemer and want to bring it anytime between Monday through Thursday, after I give it to you, I'm there basically from 8 to 6 every day except the day that I'm here. Okay, and I'll leave there at 4 to get here at 4:30. So anytime but 8 to 6 except for Wednesdays when I'll be here, you can bring it to my office there. And I put it in my syllabus where the office is. The A building is on the Bessemer campus. Not an easy building to find your way around. So if you do need directions, please ask and I'll give you directions.
Yeah, because I had to ask my little last time I was there.
Yeah. You look for me?
I get my test.
Uh-huh.
This was my second test I had. Came and got it from you over there.
Uh-huh.
I had to find somebody to help me when you find your place.
Right. The building was put together in pieces, and one piece is numbered one way, another piece is numbered some other way, then the piece in the middle is numbered some other way, then the newest part is numbered another way, and there are 3 levels of the first floor, 2 levels of the second floor, and only one little section has a third floor. And the part of the second floor I'm on is on the same level with part of the first floor of the newest part. So it's just sort of nuts trying to find your way around there. Once you know it, it makes sort of sense. No sense, but you know how to find your way around. All right. Well, then, that being said, let's move on to any questions, anything you've done so far. All right. we're in 17.8, or at least that's my mark, okay, right at the beginning of 17.8, and this is parallel circuits. Now, if you recall, series circuit, the current goes through every element of the circuit. So it's the same current throughout the circuit. The voltage supply is usually here, and the load is here, and it may be in several pieces, but you just add those resistances together, but the current is the same. The voltage is the same. Now, the voltage is supplied by the voltage supply, drops over each resistor. Okay? That's a series circuit. Parallel circuit is different, however. Okay? And this is let me first give you a definition for parallel circuit. It's in your text in bold print. An electric circuit with more than one path for the current to flow. Remember, in a series circuit, all the current flows the same path. Okay? With more than one path for the current to flow is called a parallel circuit. More than one path. That's the key. So here's an example. Okay? Here's your battery, your power supply, your voltage source, your energy source, whatever you want to call it. It gives the energy to the charges here. That's the voltage. Now this is a switch. No big deal about the switch here. But you see the current that leaves here, comes up here, can either turn this way or continue. And if it continues, it can either turn this way or continue. So you could have three different currents that add up to be this current coming out of the battery. One that goes through this resistor, a different one that goes through this resistor, a different one that goes through that resistor. And then they come back together, add back together, and then come back to the battery. The currents add. In a series circuit, the current's the same throughout. Okay? Now, parallel circuits, not. Now, another thing about a series circuit, if you were to pull out a resistor in a series circuit, you leave an open circuit, everything shuts down. If you were to pull out this resistors here, then these two stay lit because there's still a pathway. Pull out this one, these two stay. Pull out this one, those two stay. Pull out two of these, that one still works because there's a separate path to get to it. You pull out anything in a series circuit, you've opened the circuit. Nothing else works. Do you remember the old Christmas tree lights? That when one bulb went out, the whole string went out. Yeah. That was series. Okay? Most of them today, if a bulb goes out, well, they stay lit. That's parallel. Just like the lights in this room. Obviously, something's wrong on the switch there. This bank of lights doesn't come on. Okay? But the others do. So it's perfectly fine. That bank doesn't come on. But that doesn't put it all out. These are all connected to the switch in parallel. However, the switch is in series with all of them because if you open the switch, they all go out.
So, like, if you have, like, if no lights come on at all, it could be the switch or it could be something else.
Yeah, it could be just about anything, like a circuit breaker or a fuse, whichever you happen to have. Yeah, we have a thing in our garage.
That's what I'm having issues with.
The whole thing, the outside thing doesn't work, the plug inside, I think it's a new circuit breaker, okay? Because there's a switch, there's a night light that comes on or off that's separate from the thing, nothing's working, so I think it's a circuit breaker. Yeah. I just haven't repaired it.
That may be what it is, because my light in my garage is the switch. Like, I used to hear like a little popping sound in it, but then eventually it just went all the way out. Okay.
That popping sound was trying to tell you, fix me! Yeah. Mine has been yelling that at me for years, but silently because it's not working. All right. Now, this is one way to express it. Here's another way. And, sort of the definition looks like these resistors in parallel with each other, in parallel with this. Same thing here, just drawn a different way. Leaving here, the current can turn up this way, can go straight, or turn down that way. Three separate currents leave here, go through each resistor, and then come back together, add back together, going back home again. That's a parallel circuit. Three different pathways, or two, or seven, or whatever. Different pathways to get there. Now, I've already hinted at something, and here's another. The voltage across here is whatever the voltage is, whatever that happens to be. Let's say it's 3 volts across there. Well, there's 3 volts across this, 3 volts across this, and 3 volts across that. That wasn't true in the series circuit. Series circuit, you had a voltage drop across the first one, another drop across this one, another drop across this one. Those 3 drops added up to the total that's supplied here. Here, whatever is supplied here is supplied there, and there, and there, because you see these are all have pathways directly to the power, so therefore they have the same voltage across them. So, series circuit, same current through the whole system. The voltage splits between the various resistors. In a parallel circuit, 3 different currents through the 3 different resistors, and the voltages are the same across each. Okay? Same here. The voltage across this one is the same as the voltage across this, that is the same as the voltage across there. Nothing else to drop the voltage. Okay.
Why is that one so sitting up like high at B?
What's that?
Why is B sitting up high at the top?
It's just how you draw it. It doesn't matter. You see, you have a route for the current to take in all 3, just like you do here. Okay? It doesn't matter how you draw it. In reality, they could be scattered all over a room. For instance, I'm plugged into that outlet. Someone could be plugged into that. You're probably plugged into one, or are you?
No.
You're not. But you know, anywhere there's an outlet, and just because I unplug doesn't mean it cuts you off. Those are all parallel with each other. Same voltage across each, because everyone's expecting 120 volts when they plug in. And you get it, because they're parallel with each other. Okay. Now, the old Christmas tree lights? No. All right. Now, what I was just saying, oh boy. Let me write down here, this is in your text. They draw a separate picture. I'm going to use the one that they got here. Okay. Get my pen back. Okay. The voltage across this, just like I said before, V1, this is the power supply, which this book calls E. Other books call it V, but this is V1, here's V2, here's V3. Okay, the voltage across there. All of these are equal to each other. Okay? Now, the current, however, if this is a current I, leaving the battery here, part of it goes here, we'll call it I1, part goes here, that's I2, and part goes here, which is I3. And then they come back together being I adding up. So what we have is I is equal to I1 plus I2 plus I3. And if you had more, just keep adding. Whereas E is equal to V1, is equal to V2, is equal to V3, the same voltage across all 3. Okay? Now, they list that several different ways there. And I can't see what's the difference in figure. Well, I see what it is. They've added the exterior voltage. Here is the strange thing about parallel circuits. Okay? And it kind of makes sense if you think about it. Okay? The same voltage is across each resistor. That means the voltage drop here is, if you remember what Ohm's law says, voltage is current times resistor. So it's I1 times R1, that's this, and that's also E. I2 times R2 is also V2, which is E. I3 times R3 is also E, same as the others. They're all the same voltages, okay? Now, so you got, leaving here, you got a total voltage of total current of I. So when the system is looking at this, just imagine this was, you got a big current going through here because I1 plus I2 plus I3 is equal to I. And that's what the voltage sees leaving. So what does it see over here? A big current means a fairly small resistor. So whereas in a series circuit, you add the resistance together and get the total resistance. Here, you add the reciprocal of the resistors together. Because you see, the voltage drop here is, like I said, R1 times I1, and you do that for each one. So basically, because you add the currents, then it effectively means it seems like the resistance is less. The more you add, the less total resistance. It doesn't make sense, but it's true, and therefore the more current you're having to supply. Well, that of course does make sense if you think of it in terms of what's it doing to your circuit. If I plugged in a space heater in that plug, I already got my computer in that one, and then we plug in maybe another space heater here, and maybe also a television set there, and then every place in here, we plug in something that's taking a lot of power, then what's going to happen? Yeah, you're going to flip a circuit breaker, okay? And what that means is you got too much current going through the system, okay? Because every time you add another resistor, this battery is having to supply more current to go through that, okay? So every time you add a resistor, more current's required, so the battery thinks the total resistance has just gone down because the overall, the effective resistance here times this current equals that. And if you add another resistor and have to add more current, that makes it think like there's less resistors in the system. Okay? It's a weird concept, but that's indeed what's happening. So that leads to the third, fourth green block here, and this is how you add your resistances, by reciprocals. 1 over the total resistance, or I like to call that effective resistance. The book just does it R. That would be 1 over R1 plus 1 over R2 plus 1 over R3, and you keep adding as many resistors as you have. This one only has 3, those two only have 3, so you would stop at 3. Okay. Now, the strange thing is the effective resistance of the system is less than any of the resistors in the system. And the more you add, the more it drops. Because you're having to supply, the poor old battery's having to supply more current with the same voltage, so it thinks there's less resistance out there. Because there's more pathways for the current to go. Okay?
I have a question. Why do they put like the little reset buttons on the
okay, yeah. Those are, okay, it's a safety feature. And y'all probably don't remember, you're too young, but back, y'all don't even remember a mystery series called Alfred Hitchcock Presents, okay? He was a really famous director who could make some really spooky, scary, but realistic seeming movies. Not just horror stories. He wasn't into that. He made things that made you think, and it just scared the mud out of you, because of what he did. Well, back then, one of the most famous ways of someone committing the perfect murder was to, if the person they were trying to murder happened to be in the bathtub, drop a electrical appliance in there, and they electrocute, Well, those little buttons there, okay, now, several things. Let me step back even further. Originally, they just had 2 plugs, and the power either came in one or out the other or whatever. Okay. After a while, they put one safety feature, which was the ground plug. The third plug that, the 2 are like this, and then one is sort of a rounded one, either up here or down there. That provided a way to drain off if something was about to short out. but that wouldn't be enough to keep you from electrocuting in the tub. So what the third one is called a ground fault interrupt. And what that does is when a sudden surge of current hits, like you drop the toaster into the bathtub or something like that, hair dryer, whatever it was, and then you have perfect, almost zero resistance, and lots of current goes through there, and that's how they electrocuted somebody. As soon as that surge of current happens, then it breaks. It has a little circuit breaker in it that breaks the circuit. And that's why it is. So you'll find those usually in one of 2 or 3 locations. Yeah, outside,
I have them in my
kitchen and the bathroom, right? Any place that's likely to have water close by. Kitchens, bathroom, and outside where it could be rain. Okay? And that will trip the ground fault interrupt is what it's called, GFI. Those are called GFI plugs, and they have that. And that's why you reset them. If they do trip, take care of the situation, press it, and it should reset.
Right.
Yeah. So I know exactly what you mean. At the little 2-bedroom bungalow we built over on the farm when I inherited the land after my mom's death, they put GFIs on all the external plugs. So there's one on the back porch, 2 on the front porch, and 1 on the screen porch. But what we didn't know, they're all connected. And and if one of them pops, you can press the button and nothing will happen unless you get to the mother one, okay? And that one, we never, okay, it was on the back porch, and you do that, and then they all come back on again.
Sometimes it just drives me.
It really does. My younger brother actually was an electrical engineer. He hated ground fault interrupts. He said they really don't do that. They're not that good, and they're just a pain in the neck to deal with. So he shorted all his out in his house, which he shouldn't have done, and he was quite willing to do it in ours. I said, no, leave them. Okay. But a couple times when one of them has gone out because of rain or something like that, I found it the first time. I forgot about it the second time and couldn't figure out why in the world I couldn't get the GFI to come back on. Because when I'm vacuuming the porch, I like to plug into the porch, and I couldn't get it to work. So I had to plug inside, run a drop cord to go around. And then we remembered it was on the back porch. Yeah. Okay. So they can be a pain, but not too bad. Now, they give an example here of just a 2-resistor, parallel resistor system. And let's do that one. When you get 3 or more, you can still do it, but it gets harder and harder. Okay, 1 over R is equal to 1 over R1 plus 1 over R2. Okay? Now, if you were trying to solve that equation, you would have to get least common denominator here, which would be R1 times R2, right? Okay, for this to be this, you'd have to multiply this one by R2, so you multiply the numerator by R2 as well. Multiply this one by R1, but have to multiply the numerator by R1 as well. So then you have least common denominator, or common denominator of R1 times R2, but this becomes R1 plus R2, okay? And that would be 1 over R. Well, the effective resistance would have been the reciprocal of that, so R would equal R1, R2 over R1 plus R2. Okay? Now I want somebody to make up a resistance. Any number you want to. Give me a resistance for R1. Just make up a number. Anybody? What'd you say? 10. Okay. Make up one, and that'll be 10 ohms. How about R2? What would that be? Make up another one. 20 ohms. Okay. All right. Then let's see what the total resistance. Do you think that should be more than 10 ohms, more than 20 ohms, more than 30 ohms, or less than 10 ohms, or between 10 and 20, or what? More than 30? Between 20 and 30, or more than 30? Okay, sure enough, if you were listening, it is less. Let's try it. R1 times R2, that would be 10 ohms times 20 ohms divided by 10 ohms plus 20 ohms. Well, this will be 200 ohms. 10 times 20 is 200 ohms divided by 30 ohms. Okay? Okay, I'll make this a little easier. Just divide out. 20 divided by 3 would be 6.6. Let's just say 6 2/3 ohms. So what's the effective resistance? It's less than the 10 ohms. Certainly less than 20. Less than the least of the two. Okay? That's, yeah. That doesn't seem to make sense. You have 10 ohms here, 20 ohms here. Effectively, you've got less than either one of them. Okay? But that's how it works for parallel circuits. The more things you add, the more you drop the overall resistance, which means you can get more and more current, and you can overheat something and blow a fuse. I did this, and we have a little greenhouse out in back of our house where we store our plants, not the most valuable ones, but the ones we're trying to keep over winter, and put them in there over winter time. And then if it really gets cold, we were going to put a little heater in there. And then my wife heard somewhere that the old Christmas lights, not the ones that are on series, but the old lights that got really hot, people don't like to put them on trees anymore because they dry out the trees and they could catch them on fire because they get too hot. Nowadays the lights are pretty cool lights, you know, they're LED lights. But the old incandescent light bulbs, those were hot. People don't use them anymore. She found out if you strung those together, you could keep your greenhouse warm, and it looks nice too because you see all those colored lights inside. So we went to my brothers and my sister and asked if they had any old Christmas lights that were too hot they didn't use anymore. Oh yeah, we got some that we were going to throw them away. We just haven't done it yet. So I got a bunch of those together, brought and put back, and it's a real small greenhouse. And I found out if I just ran one cord and did strung one cord to another, I blew a fuse. The reason is those were in parallel, and if I do too many. So what I did, I got me one of those cords that has 3 prongs. So I could do 2 on this one, 2 on that one, and 2 on that one, and it wouldn't blow a fuse. As soon as I put a third one on, it would blow. So I had to be very careful there. The new lower wattage lights, you can string almost as many of them together. You can't. There is a limit, but that's because they're such low current draws anyway. They produce so little heat. So that's what we have with your parallel circuits. Now, there's a comparison for parallel circuits. There's a water system that they're going to show here. Okay? Now, let's see what we've got here. Remember, we had a water system for the water pump analogy before. We can do parallels, too. Let's say we have a pump here that's like our battery, giving energy to the charges. Okay? That's what voltage is, energy per unit charge. And rather than current, we have water flowing through, but it's a lot like our currents here. Okay? Well, if you take this pipe here and split it into 3 smaller pipes, well, each one is offering some resistance because they're smaller in size, but because you have 3 total pipes for it to go through, this is actually bigger than what you had to begin with. So actually, overall, there's less resistance than any one of the 3. So there's the analogy there. Your battery here, your pump here, your water flow here, your current here, and because there's even those resistance in every one of those, because there's 3 different paths you can get there, you actually have less resistance overall. And if you add another one, that's even more pipe for you to go through, so the resistance drops off. And some current goes through this one, some goes through that one, some that one, just like we described here. So it's a pretty good analogy to the water pump model. Does that kind of make sense? Okay. Here are the summaries of that. The total amount of water flowing through R1, R2, and R3 has to be the same as coming in or leaving. You don't add any water, you don't create any water. Same water is flowing through, being pumped by the pump, is add the three currents together. The water flowing past point A, which is this end of it here, divides into three branches, R1, R2, and R3. So that's the same thing here. The current I goes into I1, I2, and I3. Okay? The larger pipes have less opposition to water flow than do the smaller pipes. Okay? So even though each one of those little pipes is more resistance than the big pipe, when you have three of them that the water can choose to go, the total area is greater than they were if there were only two or one. Okay? Now, with a parallel circuit, the total amount of current coming out of the battery is I, but when it gets down to the junction A, it splits, and some goes to I1, some goes to I2, and some goes to I3. Same as we talked about before, the smaller resistances have less opposition to the current flow and therefore carry larger currents. Okay. Let's move to, and they do talk about parallel bulbs, and there's a little activity. If you have the things, you can try it. But let's do example 1. Okay, let's see if that's in the, okay, this is a summary slide. So what I think I'll do is go back to this slide. I'll erase what I've got here, and we'll use this one and have R1 equal 7.00 ohms, R2 being 9.00 ohms, and R3 being 12.0 ohms. Okay? Now, the question is, what's the effective resistance or the total resistance, the overall resistance? I would say effective or overall. Total to me means you add.
Right.
You don't add. So you call it effective resistance. What is R? What's the formula? Do you remember?
1 over.
Yeah, it's reciprocal. 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. That's the formula. Here's what we put. 1 over 7. I'm going to leave off the 0.00. We'll come back and put them in at the end. Plus 1 over 9 plus 1 over 12. Now, do you want to do least common denominators and all that mess with this? Please say no. Okay, good. All right. I'm going to show you how to do it on the calculator. It's a really handy thing to do. Do all of you have either a calculator or a phone that you can do it on? Okay. Find on your calculator a key that's like this, 1 over x. It may be like this, x to the minus 1. It's usually going to be one of those two keys. If you can't find either one of those on your calculator, let me know and I'll see if I can come find it for you. You got it? You have it? You can't find it? Okay. There may be a different name or something. My eyes are so bad. I have to get a, oh, there it is. X to the minus 1. Right there. I think that's what it says. Okay. So, did you find one of yours? Okay. All right. So what you do, you type 7 and then hit that key, X to the minus 1. That reciprocates it. Plus 9, hit that key. Plus 12, hit that key. Do an equal sign. That gives you 1 over R, so hit that key again, and it flips it up and tells you what R is. What do you get?
I got 252 over 85.
Say again?
252 over 85.
252.
Uh-huh.
Ooh, let's try that again.
Let's try this again.
Okay, let's try it again.
Okay.
Anyone get anything else?
I had got like a 0.3.
Hey, you probably
okay.
were right.
Oh,
Okay.
I erased it well.
Did you get anything? Okay, let's try it again. 7 times x to the minus 1, or 1 over x. I mean, hit the key. Don't do times. 7, hit that key. Plus 9, hit that key. Plus 12, hit that key. Equal, and then press that key one more time.
0.337.
Okay, 0.337.
Just equal one time. No, I hit. They didn't keep giving me that.
Okay, they still didn't quite get it right. Okay. Let me see you punch it in.
Oh.
Okay. Okay, hit equal one more time. Hit equal one more time.
I just hit my key one time. I don't know why it's giving me that.
Yeah, that's it.
It's giving her like a It ain't doing
If
it
you
right.
got the .33, is that what everybody got?
No, hers is not doing it right.
Okay.
Let me out. I put it in, but it's not doing
right.
it.
There. Okay. So it's 7.
50
Hit the key.
plus 9.
Plus 9.
Hit the key.
Hit the key.
Plus 12.
Plus 12.
Then hit the key.
Hit the key.
Hit equal.
And hit equal. Okay. That leaves it a fractional form. Then hit the key.
Oh, I need to change it from a
Then,
fraction?
no, wait. Then hit the key again and press equal. And there, let's see if.
Do I hit that button right there?
Wait. Okay, wait. What does that do for
That
you?
changes from a fraction to a decimal.
Which one?
This one.
Okay. Yep, 2.96.
Okay.
That's it.
So why is it showing what you was about to say about the 333?
Okay, if you had that, you hit equal one more time. Because it says answer to the -1.
Mine don't do equal again.
Huh?
It don't do equal again past that.
Okay. Well, then hit your 1/x key again. So your x -1 equal.
Oh,
There.
okay.
Yeah.
Well, let me write it down because if I'm working this problem at home, I might forget.
Forget
So you have to reciprocate that one last time. Okay. All right, and that's what the book got to, 2.96 ohms, which is, by the way, wait. 1 over that. The 1 over R is that small number, and then R, when you hit that last time, which you may have to hit an equal sign. Some calculators do, some don't. That is 2.96, which is less than any one of those. Way less. Okay? The more you have, the smaller it gets, which is so bizarre. Okay? So that's example 1. And they do show you in the book, if you got your text, at the top of the page, 7x to the -1 plus 9x to the -1 plus 11 plus 12x to the -1 equal, and then you hit x to the -1 again and put another equal. Okay. I forgot to tell you that last equal. All right. So let's go to example 2. Find the total current in the circuit shown in figure 1714. So I'm going to use this one here because it looks like that. Here's your E is 90 volts. And by the way, that's not batteries. I can almost guarantee you that better be AC because you don't usually get that big a voltage. But that's not beside the point. Here's your R1 of 23 ohms. Oh, and by the way, here's where we get our units back. When you had your calculator and gave you a whole bunch of units, just pick the first 3 unless the one next to that third one was greater than you up it by 1. So I just didn't write them in there. Okay, R2 was 14.0 ohms. And R3, 5.00 ohms. Okay. Now this time it says what's the total current in this system. Okay. Now you have 2 ways that you could go. Okay. You can do either way you want to. I'll tell you both of them, but I'll tell you which ones that I think is the easiest. You might be able to figure it out too. Because the same voltages across each of those, you could do E divided by R1, that would give you I1. And E divided by R2 would give you I2. And E divided by R3 would be I3. And then added 3 up, and that gives you the total current, I. Now that's doing 3 multiplications, 1 addition to get what you need to get. Or you could find the effective resistance here. 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3, where this is 1 over R is equal to 1 over 23 plus 1 over 14 plus 1 over 5. And that gives you, then you have to hit it one more time to get R, the reciprocal one more time, and then divide that into E, and that will give you your I, your total current. So either way you want to do it will work. You want to try it both ways, or you want to do it just one? Or one of you want to do one way and the other two do it the other way? How you want to go?
Yeah, I'll try the bottom one.
You're going to do the bottom one. Okay, well, let's everybody do it. It's pretty easy because we need the practice. 23 x to the minus 1 plus 14 x to the minus 1 plus 5 x to the minus 1 equal, and then you get an answer, and then press x to the minus 1 again and equal. And what do you get?
3.175.
3.175. Now, I'd hang on to all those digits that you got, and then take that number, and this is going to be a little tricky. Take that number, that's your R, I'm sorry, this is the R, not R is equal to that 3.175. If you hit that reciprocal one more time to put it in the denominator, and then multiply that by E, which is 90, see what you get.
Hold on now, okay, I'm still on the number, the 3.17.
Yeah, whatever is on your screen, hit the reciprocal one more time to take you back to what you had before you did that last time. Multiply that by E, which is 90, and what do you get? Say again?
Multiply it by what?
90, which is your E. See, what you're coming up with is 1 over R, multiply that by E, and that gives you E over R. And by the way, they got 3.182, but, okay, what do you get for your I?
28.3.
28.3.
Okay, I thought it was too big. I thought it was one button.
Me too.
And that's in what units?
The
Current? Amps, amperes. Current is measured in amperes. Okay, let's do it the other way. It's still easy. 90 divided by 23. Okay, plus 90 divided by 14. Plus 90 divided by 5 equal
28.3.
28.3. See, both ways work the same way. Okay, so it just depends. The other one you had to enter 93 times. This one you only had to enter it once. But pay your money and take your choice. You've already paid your money. You just which way you want to do it. Okay, so 28.3 amps. Okay, now before we leave, oh no, we need to go to another figure. We'll go back to the first one. So is it all right for me to erase? Okay. All right, we're going back to the first figure. Wait, no, maybe we're not. Figure. Oh, no, I just blew it. The one I just had before, but we had already done it. What was the current through R2? I'm sorry, I thought it was the next one. Well, remember R2 was 14.0 ohms. Well, it doesn't matter what the other two were. The voltage across here is, E was 90.0 volts. So take 90 divided by 14.2. Remember Ohm's law? E is equal to IR. Or you can write it the other way. I is equal to E over R, or R is equal to E over I. You can do your circle or your triangle. There you can get all three of those. what we're looking for now is I is equal to E over R. Voltage across there is 90, divided by the resistance of 14. What do you get?
6.338.
Say again?
6.338.
Yep. 6.43 you said?
Yeah, 6.34.
90 divided by 14.
Oh, I don't know why I get 14 points.
Oh.
6.43.
All right, 6.43. I2 is equal to 90.0 volts divided by 14.0 ohms, which is equal to, what do we say, 6.43 amps. Good deal. Make sense? All right. Sorry, I should have left that other one up there. Okay, now move to example 4. Find the equivalent resistance and the value of R3 in the current shown in figure 1745. So that's a lot like the first one here, so I'll put it in. Your E here is 115 volts. That's AC for sure. Your total current that you have flowing here is 7 amps. Let's just draw it here. I is equal to 7 amps. Total current. Your R1 is 38.0 ohms. R2 is 49.0 ohms. And R3 is what we're looking for. Okay. But, as they say here, find the equivalent resistance first. What's the equivalent resistance? Ohm's law. R is equal to, oops, don't use that one, I wrote it wrong. What should be there? E over I. We got the E, 115 volts, and you got the total current, 7 amps. So what's the effective resistance? Punch it in and see. I probably should have put 7.00 amps, but okay, let me clean this up a little bit. I've got in too big of a hurry there. 7.00 amps. Okay, what you get?
16.4.
A little out of 16.4. And that would be ohms. Okay. Now, this is going to take a little more effort to think through, but I'll guarantee you this, R3 has got to be more than 16. I'm going to just guess 20, but I don't know that for sure. That's just a guess. It's got to be more than 16 because your effective resistance in a parallel circuit is always less than any of the lowest resistances. Okay? But what we do know that 1 over R is equal to 1 over R1. Tell me the rest of it.
R2.
1 over R2 plus 1 over R3. And since we're looking for R3, we just subtract the other two from 1 over R. So 1 over R3 is equal to 1 over R minus 1 over R1 minus 1 over R2. You see that? So we know what those are. 1 over, what was 16.4? Or whatever is still in your calculator.
16.4, yeah.
Okay. Minus 1 over 38 minus 1 over 49. Okay? That will give you 1 over R3. So do that and see what you get. And once you do it, then hit that reciprocal key one more time and an equal, and that should give you R3. This time it's minuses, not pluses. Second?
70.6.
70? Okay. You got R3 is equal to 70.6. It could be, that seems a bit high, but it could be. It could easily be that. Let's see what they got. Well, they got 70.2, so it's probably just a round off error.
Yes, it's rounded up.
Yeah. Yeah. So I was guessing 20. I was way off. It just had to be greater than your effective resistance, which was 16.4. Make sense? They got 70.2 ohms. Okay. Now, my guess is they used the 6.43. If you just use the reciprocal of what you had, yours is more correct than theirs. Okay, so I would go with yours. Because you see, they rounded off once and then they're rounding off again. That's 2 round off errors. You only rounded off the last number. Okay. And they show you the key entry sequence at the top of page 471, exactly what we just did. 16.4, x to the minus 1, minus 38, x to the minus 1, minus 49, x to the minus 1, equal, x to the minus 1 equal again, and 17.2, 70.2, we got 70.6, because we did it better. Okay. Any questions on that? Everybody get about that same answer? Okay. And let's go to the summary slide, which is here. This is the characteristics of parallel circuits, what we just said. Remember, in a series circuit, the same current is throughout. I is equal to I1, is equal to I2, is equal to I3, is equal to all those. Parallel, no. Each branch adds to make the total current. Okay? Doesn't happen in series that way. Same current flows through everything. Resistance, however, the weird one, is a reciprocal relationship. 1 over R, the effective resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus ... Keep going. The voltage, though, whereas in a series circuit, the total voltage at the beginning is equal to the sum of all the voltage drops at the end. Here, it's the same as all the voltage drop, not the sum. So E is equal to V1 is equal to V2 is equal to V3, as many as you have. So that's your summary slide for your parallel circuits. Okay. Now.
That's a long chapter.
This what?
Long chapter.
Yeah, it is. We're not going to do all of it. In fact, okay, that did finish 17.8. There is a problem set at the top, which is only 4 problems, so you can do 1 and or 3. That's all that have answers in the back. And some of these have more. One of them has 4, one of them has 2, 2 of them have 3. Now we get to compound circuits. Circuits that have kind of combinations, okay? And this is part of example 1. A compound circuit contains a combination of resistances, some in series and some in parallel arrangements. To simplify solving this kind of circuit, we apply rules for series and parallel circuits to find equivalent circuit that reduces to a circuit with 1 resistance. Okay? So here's what we're going to do. Here we have a circuit, and on the top part, it has 2 resistors in series, but they're in parallel with the one on the bottom. So what we do is first find the total resistance of these 2, and since those are series, you just add them together. So that gives you R4. Add these together to get R4. Now we have 2 resistors in parallel. Use the parallel resistances, which is your 1 over R. That would be 1 over R5 is equal to 1 over R4 plus 1 over R3. Okay? And that will give you the R5 when you hit that last reciprocal key. Okay? So first you just add those two together to get R4, then you use a reciprocal relationship to get your R5. So how do you eat a 5,000-pound elephant? One bite at a time. So don't try to swallow the whole thing. Take each little piece, do it, and then simplify, simplify, simplify until you get a total resistance. So what they're asking you to do in example 1, the circuit B, that's the middle one there, is equivalent to circuit A, but R4 is equal to R1 plus R2. Then circuit C is equivalent to circuit B, but now you have 1 over R5 is equal to, so I just didn't write this, let me do R1 plus R2 is equal to R4. That's the relationship to get there. Then you use your parallel relationship to get R5. Okay? Now, I don't see the problem here yet.
Is it in the middle of the page? On 479?
Okay. It's just showing this diagram here. I guess the problem was filling in what I filled in. R1 plus R2 is R4, and 1 over R5 is 1 over R4 plus 1 over R3. I guess that's all there is to it. Okay. There's no answer, so to speak. Okay? Except that. That's how you get there. So example 2 is a different one. Let's see if we have example 2. Ah, here we go. All right, here's example 2. Circuit B, the middle one here, is equivalent to circuit A, but this time to get R4, you use your parallel situation. So 1 over R4 is equal to what? 1 over R2 plus 1 over R3. Perfect. And so you do that one first, and then how do you get from that to C? Those are in series, so you just add them. R1 plus R4 is equal to R5. You see? Parallel, you do reciprocal relationships. Series, you just add them. Right? Okay. I think that's all you had to do with that one. Okay? Now we're ready for example 3, which we don't have. Okay. Yeah, the one with numbers we don't have. Find the total current in the circuit shown in 1753. That's
How they gonna have it in the book, but now
all right.
PowerPoint?
All right. Oh, this PowerPoint is just so pathetic. But here's what we're going to do. You see the one in 1753 is basically this circuit right here. You just have to add to it a power supply here, E, and that E is equal to 115 volts. Okay, and then loop this around and bring it up. There we have it. Kind of ugly, but we got it. Okay, it said find the total current. The total current will be this I here, the I that leaves E and goes up this way. Well, how are you going to find the current? You got to find the equivalent resistance first. So we do the same thing we did. Oh, let's fill in the blanks. R1 is 10 ohms. R2 is 32 ohms. And R3 was 19 ohms. Okay, so the first thing you got to do is come up with the equivalent resistors of that whole circuit there. So which you do first? R1 and R2, and what do those add to be?
There's going to be 42.
42 ohms. So R4 is 42.0 ohms. And R3 stays 19.0 ohms. And then how do you find R5? Is what? You may have said it right. I just can't hear well.
Oh, do you add R3 and R4?
These are parallel, so you have to do the reciprocal. Okay? So you got 1 over 42 plus 1 over 15. No, that's 19. I can't read my writing. Okay, sorry about that. Why can't I get it to erase? Too much erased. Get out of there. Okay. What does R5 come out to be? Guarantee it's less than 19.
13.
Sounds reasonable. 13.08. Okay, let's leave it there, and that would be ohms. Okay, now that you know the total voltage and the effective resistance, you can calculate what I is. I is what? Tell me that by Ohm's law. First, give me the formula.
It's going to be 1 over.
No, wait. I. Current Ohm's law. No, you know. E over R. Remember?
E over R.
You like triangles or circles? E is equal to I times R. Okay? If you're looking for I, it's E over R. And your E is? Yeah, 115 volts. And your effective resistance, which is your R5, 13.09. All right, to use extra digits there. And that's ohms. And what would that give you?
No, how do you get 13.09? It's supposed to be 8.
Huh?
It's supposed to be
8.08.
8. 13.08.
Okay, that'll be fine. I don't care what you use. Just use it right.
8.79.
8.79. What unit? Current? What's the unit for current? Louise? Ampere. Amps. Okay. See what they got? Whoa!
Did we get the wrong thing?
No. They did it right. Okay. I just had to turn the page. What you get? 8 points. They got 8.78. You got 8.79. Close enough. What is 1/100th of an amp among friends? I mean, nothing to write home about. Okay. Whoa here. We got an example 4 that I really don't have a slide to match. So let's just go to another slide and we'll draw our own. Okay, here's example 4. Find the equivalent resistance of the circuit shown in 1754. Okay. Oh, goodness, I ever have to change my color back. Okay. Here's your voltage source of 120 volts. That, I say volts and I write ohms. Duh. Okay. All right. Now it comes up here and hits a node, and one goes up here to R1. One goes across here to R2. One goes down here to R3. And they leave here and come down to come in here. And one goes here to, I guess this is probably R4. And one comes down here to R5. And then we go back home to that. So R1 is equal to, 7.00 ohms. R2, not D2. Goodness gracious. It's 35.0 ohms. R3 down here is 25.0 ohms. More of these I draw, the uglier they are. R4 is equal to 20.0 ohms. And R5 is equal to what? 62.0 ohms. All right. Now, what we're looking for, find the equivalent resistance in this circuit. Guess what, team? You don't need that 120 volts at all. I bet you the next problem we will, but this one, you don't need the 120 volts. Because it doesn't say anything about current or anything else. It just says, what is the equivalent resistance? So what are we going to have to do?
Do all the R's first.
Okay. Do this set of R's first. And what does that give us? I mean, how do we do that one? Those are in?
R.
Okay, that's your reciprocal. These are in parallel. So it'd be, okay, we're going to call this effective resistance here R6. Okay, so 1 over R6 is equal to what?
R4?
That's down here. We're dealing with these up here right now.
Oh, so, okay, you doing 1 over R1.
Yeah, 1 over R1.
Okay,
plus
1 over R2.
R2 plus 1 over R3. And plug in the numbers. That's 1 over 7 plus 1 over 35 plus 1 over 25.
Too many numbers.
See what we're doing? Finding the equivalent of that parallel leg up there.
That's just the first part.
That's just the first part.
My goodness, let me see. $4.729.
That sounds reasonable. So R6 is about 4.729. Doesn't hurt to have extra digits now, and that also will be in ohms. And what do we do next?
Then you have to, so this, you have to do R4 and R5.
Okay. And how would you do those?
Just add those together, right?
What kind of circuit is that? Parallel or series? Is it?
Parallel?
Well, look at it. The the resistors are parallel to each other. They're not in line with each other, they're parallel. Okay, so that's parallel. So what rule do we use? Okay, let's call it R7. 1 over R7 is equal to 1 over R4 plus 1 over R5. Okay, which would be 1 over 20 plus 1 over 62. Second, 16?
15.
15 point what?
12.
1, 2 ohms. Okay. Now, if we were to redraw this circuit, I'm going to have to draw it a lot smaller because I don't have room. But here's my battery here, we still don't need, but we know it's E is equal to 120 volts. Okay. Instead of this one, I'm just going to put R6. And then down here, instead of that one, I'll put R7. Now how are those related? Second?
Not parallel, right?
They're not parallel. They're in series because the same current goes through all of them. So those are in series, so you just add them together. 4.729 plus 15.12, that's going to be 19.85, which is going around to 19.9 ohms. Is that what they asked for?
Well, you said the
They said 19.8. Huh?
You said the 62.0 plus that, the 15 point.
Yeah.
Okay.
This one, 4.729 plus 15.112. 6 and 7.
I see it.
When they're in series, you add the resistances. The book got 19.8, which is close enough. They put 8.3 and then rounded it to 19.8. And they called that, by the way, R8, which is the effective resistance of the whole system. Okay. Now, example 5 says don't erase anything because find the total current in this example, example 4. So how are we going to get the total current? Now we're looking for I, which is the same as this I. Same thing. So how do you get I?
It's going to be, E over R.
E over R, perfect. And that's the effective resistance, which is our R8. And that's going to be, what's our E?
E is going to be the
120 volts divided by 19.8 or 9, whatever you want to use, ohms. And that gives you approximately a little bit more than 6. All right? 6.06. Yeah, 6.06 amps. Okay.
getting pretty long.
What's that?
How you get 16.6?
It's 6.06.
Oh. Well, I don't got that neither.
What's that?
I don't think I got that neither. I have 6.0.
Wait, okay. 6.03? That's all right.
Okay.
That you see, they've contributed a lot of round off error. We haven't done as much as they have. So I like, yeah. Okay. And one thing they did that I didn't do, they put a bar over the 0 there. meaning all 3 digits are significant, which we were doing 3 digits anyway. All right, 16.06 or 03 or something like that. All right, that leads us then to the next slide here, which are characteristics for a series and parallel circuits. We've had them separately, now they put them in one table. So, good things to keep in mind. A series circuit means the same current flows through everything because there's only one pathway. The total voltage is the sum of the voltage drops across each resistor. The resistors are the sum of all the resistors. The total resistance is the sum of all the resistors. But the current is the same through every element. Okay? Not so in parallel. In parallel, the same voltage is across everything. So these are all equal. Down here, the currents add, not all equal like they are with this, and your resistors add by reciprocals. So at the very end, you have to reciprocate one last time to get your effective resistance. Okay? Make sense? Good thing to remember. Okay. Good thing to come back to. And that finished 17.9. Okay? And you can do any of the odds 1 through 5, any of the odds 7 through 11, any of the odds 13 through 19, and any of the odds 21 to 25. And they get some pretty, they may look complicated, but you remember, eat them one bite at a time. Take the simplest, combine, 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 however it is, and then you come up with your effective. Okay. Now, that was 17.9. We're not going to do 17.10. I don't think 17.11. Oops. Where was 17.11? Voltage sources? Nope. 17.12? Nope. 17.13. I don't think so. So that's it, I think, for 17. Let me go back and check and make sure I'm not leaving out something. 17, 3, 4, 5, 7, 8, and 9. That was it. You almost had to have Ohm's law, so we threw in Ohm's law. Okay? So that's chapter 17. So I was wrong. Okay? Let me go on and give you your test on chapter 17. I've got it made out. I just wasn't sure when we were going to finish. I was thinking it was going to take us longer to finish than it did. So let me give you chapter 17 test. Okay. Period, 2 charges. There it is. All right. Now, I think we're down to 9 people. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, there's one person we hadn't seen in a long time. She did show up at my office last week to pick up her other test. I can't remember why. It seems like a family issue or something like that. Several of the guys have hardly turned in anything, but I appreciate you gals. You have been very faithful to all the time. So I think we're down to 9. So let me go make 9 copies. I'll be back in just a bit. What I'm going to do, you know what I forgot to do? No, I didn't. It's home. I couldn't see my thing. Let me pause this so you don't have a lot of... All right, I turned off the sound momentarily. Just to review what we just did, I gave test 5 to everybody on electricity, and we're starting chapter 18, magnetism. As far as we get on this will be what the last test will be, which is your final last test. Not going to be comprehensive, just what we covered in chapter 18 here. I don't think we'll get to 19. So let's start from the current slide. And let me get turned over to chapter 18. Oh, by the way, I didn't tell you this, but there are some additional problems at the end of the chapter. But remember, okay, there's a glossary there, and you can look at, get a lot of the words there. Some of them we didn't go over, some of them we did, so that's not. Okay, we did do under formulas. We did Coulomb's law, 17.3. We did field, the electric field, 17.4. I think we did resistance, which is based on resistivity. Yeah, I remember going over that one. Ohm's law for sure, 17.6. And then the characteristics of series circuits and parallel circuits in 17.7 and 8. And that's as far as we went, okay? So hopefully that's all you'll need. 17.3, 4, 5, 6, 7, and 8, okay? Review questions, again, just hit the ones that we covered. Those are just mostly conceptual things. The review problems, okay, I think most of the odds 1 through probably 31 will probably be all you need. No, actually, maybe a few more. I think they're sort of mixed up in here. So you can't tell for sure just looking at them. I know through 31 should work, but then it looks like 37 should work too. No. 37 has multiple batteries. We didn't do that one. So only go through 31. And you may not do all those, but do the one that we did in class, if you want to. Those are just additional problems. All right, so let's go to magnetism. Now, here's what I highly recommend for you. Work on the test now, as soon as you can. So if you have questions, you can ask those next week, and we'll get all those questions settled. And then we'll continue with 18, and then just what we cover in 18 will be on the last test, which will be the final. Okay.
So the final day will be the first week of May.
Yeah, I'll give it to you
next week,
next Wednesday, and you turn it back to me. The following. And if you don't get it to me by the following Wednesday, you'll have to catch me on either Bessemer or Birmingham West some other time. So got to get it done. Now this one, you can either turn it in to me next week or you can turn it in with the final, whichever. Okay. So let's start with the introduction to magnetism. By the way, the sections we're going to cover in magnetism are 1, 2, and 7. So if we get these covered, we'll go on and do 19, 3, and 5. That's all we're going to do in these 2 chapters. 5 sections. 1, 2, and then jump over to 7. Okay? So let's start in 1. Chapter 18 is magnetism. And the first slide is nothing close to what you see in the book. It's on, goodness gracious, where is it? Have you found it yet? 504. 502. Oh, there it is. Yeah, I see it. Okay. So let's go with this one to start with. All right. Usually at the beginning, and the same is true here, a bunch of general stuff just to get terminology and that kind of stuff down. All right. Starting on 503, there is a picture there of a magnet. Now, how you know it's a magnet, it's labeled N and S. Okay, what do the N and S stand for? North and south poles of a magnet. Now, why would they name the poles of a magnet north and south? Well, frankly, because the Earth is one big magnet. Not a very strong magnet, but is a magnet. So if you have another magnet, it's going to approximately point to our North Pole with its north-seeking pole, okay? So that's why we call it north and south. Now, for all the time that mankind has been in existence, it's always pointed the same way. But they have discovered when they drill down core after core after core, there has been 22 reversals, or approximately 22 reversals of the Earth's magnetic field. So what was it doing in between those times? Either no magnetic field or wacko. But right now, in the time frame we've lived in, all been pointing north. Okay? Now, what that first picture shows is a paperclip being attracted to the North Pole. I can guarantee you one thing. That paperclip was made out of iron. It wasn't made out of aluminum. It wasn't made out of any other metal except iron. Most of the time we don't make our paper clips out of nickel. It could have been nickel or it could have been cobalt, but cobalt, is even rarer than nickel. So it's iron. That paper clip was made out of some iron product, okay? Because those are the only three naturally occurring magnetic materials: iron, nickel, and cobalt. Now, I'm trying to remember if this book has a periodic table in it. I have looked before and I never can remember because different book, I'm teaching from several different books. I don't think this one has a periodic table. It should, but that's more chemistry than it is physics. Let's just see if there's a periodic table anywhere in here. Oh, I know where I'll look. In the periodic table. There it is, 628 or 643. Oh, they just talk about the sixth periodic table here. So let's do, what was the other page I said? 643? Anything there? No, they have it in the glossary. That's real helpful, isn't it? Okay.
Because this book has issues.
That's a minor statement, isn't it? I thought maybe there'd be a listing of the elements, but I don't see that either. But anyway, if you were to find the periodic table, you will find that those three elements, iron, nickel, and cobalt, are right next to each other in the periodic table. Okay? And no other naturally occurring materials are magnetic but those three. Okay? Now, if you allow a magnet, suspend it from a string, say, it is going to line up and point to the north. Now, I'm not even sure which way north is. It's that way, right? Approximately. Okay? So it would point that way. But it wouldn't just point like this. It would probably do like this. Now, why? Did you have it unbalanced? No, because if you picture us, we live on a globe, right? Okay? We live on a globe, so the north, if we say that's the direction north, the North Pole is really down there somewhere, right? Because it's around the curve of the globe. So the magnet would not just point this way to the north, it points like that. Now, most compasses you have, they restrict it and don't let it point down. They let it only point horizontally. So that's why it points to the north. Okay. So, characteristics there. Okay. Metals with the ability to attract pieces of iron or steel are said to be magnetic metals. Iron ore that is naturally magnetic is called lodestone. Okay, that's one name for it. Naturally occurring magnetic iron is the old name for it is lodestone. The actual mineral name is magnetite. And you can see the word magnet right there in the first 6 letters. Okay? This is the common name. This is the mineral name. Okay? Now, magnetite has exactly the same chemical structure as hematite, which is another mineral. The chemistry is identical to magnetite. The only difference is this one's magnetic and this one is not. This one is attracted by a magnet, but that's naturally occurring magnetic. Okay? Now, materials that can be made into magnets are called magnetic materials. Most materials are non-magnetic. Okay? But it says artificial magnets can be made from iron, which is an element, steel, which contains iron, and several special alloys such as permalloy and alnico. Guess what alnico is? It has aluminum in it, but it also has nickel and cobalt. You gotta have one of those 3, iron, nickel, or cobalt. Permalloy, guarantee it has one or more of those 3 magnetic materials in it. Okay? So things that are not magnetic, wood, aluminum, copper, zinc, name it. Unless it has iron, nickel, or cobalt in it, it's not magnetic. Okay. Now, remember back when we were talking about electric, we talked about electric forces. And we had Coulomb's law. We just mentioned that as one of the equations and formulas at the end of that chapter. Coulomb's law. That talked about magnetic forces. We also have, electric forces. We also have magnetic forces. And if you remember the rules for electric things, remember in electricity we had 2 types of charges. Positive charges or negative charges. And what was the relationship between them? What if you have a positive here and a positive there? What are they going to do? Repel each other. Like charges repel each other. What if you had a positive and a negative? They attract each other. How about negative and negative? Repel each other. Okay? So you get the general idea. Well, magnets have both a north pole and a south pole. And guess what they do? A north pole does what to a south pole? Attracts, of course. And what does the north pole do to the north pole? Repel. South pole to south pole? Repel. Okay, you got it. Just like charges, like poles repel each other, unlike poles attract each other. That's the general rule for magnetism, just like it was for electric charges. Here's a difference, though. You can have an isolated positive charge. You can have an isolated negative charge. You can never have an isolated north pole or an isolated south pole. Oh, but I bet I can. Let me take a bar magnet. You've seen them, ends on this end and S on this end. I'm going to break it in 2 or cut it in 2 or whatever. Now I have the north here and the south here, won't I? No, right where you broke it, even though it was not magnetic before, if you dump iron filings on that, they all gather at the poles. They don't gather in the middle, they all gather at the poles. Okay? If you broke it in 2 or cut it in 2 or whatever, then actually where you cut this, if that was your north, that becomes the new south, this becomes the new north, and that becomes your old south. You can't do it. Every time you break them, you always are going to have a north and a south. Magnets always exist as dipoles, 2 poles. You break them and you just keep getting out. I bet you've put on your refrigerator before one of those little magnets that's about that thick. It's a round, circular, one side's positive, one side's negative, even though it's only about that thick, okay? If you cut it in 2, then you'd have 2 magnets on the, it keeps going. One side's north and one side's south, okay? So the illustration there on page 503, like poles repel, unlike poles attract. Now, just like with electric forces, you can talk about electric fields. Remember we had that formula too. Same thing with magnets. Anytime you have magnetic forces, that indicates you have magnetic fields. A magnetic field is a field of force near a magnetic pole, always concentrating near the poles, or near an electric current. Now, we'll get to that a little bit later. That can be detected using another magnet. We represent this field of force by drawing lines that indicate the direction of the force exerted on the North Pole placed in the field. Okay? Now, this is not quite going to do it, but let's see if it comes close. Let's go back to this. Now, you see these iron filings here? They almost line up according to the lines of force. Now, iron filings are just little bitty shards of iron. Okay. Have you ever seen someone when they cut wood, you have sawdust left over, right? This is like iron sawdust. Okay, it's not saw, it's just very little.
I think I've seen it on something before. It's like real fine, like gray looking.
Yeah, just really fine things. But you can tell it's iron, okay? And if you were to put a North Pole and a South Pole near each other, look, they all, as many as they can, get in between the two because the lines of force are really close there. But then you see the lines of force. These are just little bitty particles of iron, but they line up just like these lines of force, okay? But if you put north near north, you have to hold them there. See, you have to hold these apart because they're trying to go together. So you're holding them apart with the thing. Maybe you have them nailed in place or something here, but the lines of force are here. But you put north to north, and now the lines of force are pushing each other apart. They never cross there. They're like this. Here they go together like crazy. Here they're pushing apart like crazy. You have to literally force them together to get this picture done. But you see, the iron filings basically are lining up like the lines of force do. That's how we get the idea to use lines there. Now let me give you a hint here. I don't know if the book's going into it, but I'll tell you. I don't know if you remember with our charges, the field lines for charges, the field lines always point away from positive charges toward negative charges. Well, similar here, the lines of force on a magnet, I think I'm going to go with something like yellow here. It may show up better. The lines of force always go away from a North Pole and toward a South Pole, and that's why they're being pulled together. Away from a North Pole and toward the South Pole, okay? Away from the North Pole, away from the North Pole. So they're trying to get away from each other, okay, because they're pulling in the same direction. These, they're going to go together because they're pulling them together. So the lines of force are always away from a North Pole and toward a South Pole. Here we don't have a South Pole, so you can't see one. Make sense? Those are called the magnetic field lines, okay? Let's see if the next slide shows. No, I don't think it will. No. All right. I guess I ought to try to draw it. Yuck. I hate drawing these things. Okay, let me just get out of this. And why did I go back a slide? I don't know. Okay. Okay. All right. If you have try to draw it the same orientation they did. If you have let me get my pen back. Okay. If you have the bar magnet here, and this is the north and this is the south, okay? The lines of force, remember I said, always point away from the North Pole and toward the South Pole, away from the North Pole toward the South Pole, away from the North Pole toward the South Pole, away from the North Pole toward the South Pole, away from the North Pole toward the South Pole. If you look at this, you see how the field lines are really close together here, really close together there, hardly any in the middle, right? So if you put iron filing, they're all going to get right there on top of the north and south poles, and you'll see a few of them, like you saw before, line up according to those field lines. Oh, I need to put my arrows there. Always away from the north, pointing toward the south. I need probably one more this way. Okay. Always away from north toward the south. Okay. And then, and here I will have a lot of trouble showing this. I think this one I will hold up just so you can see for the, yeah, oh, I've got both. It's your figure 18.5B. You can see those lines of those iron filings just, I mean, making perfect little field lines there, all crowded around the poles, hardly any in the middle. But if you put little compasses up there, the compasses are always pointing away from the North Pole toward the South Pole. The north end of the compass is pointing that way. Okay? I can't tell which is north and south there because it's not distinct enough, but you can do that. Okay. Now, like I said before, so let's get out of this one and go back to this one. Okay. Oh my goodness. Yuck. We're out of time. We'll pick up with this slide next time. This is on page, somewhere I've got my pencil here. Right there it is. On page 505. Okay, that's where we'll pick up and go next time. Now, we almost finished 18.1, but there aren't any problems for 18.1, so there's nothing really to do here. And as I said, we're going to do 18.2. Second? Yeah, it has a few, but we aren't there yet. And remember, we jumped from 18.2 to 18.7, didn't you say? Yeah. And we will jump there. Okay. All right. So it's not going to take us long, so we might even get a little bit into 19. Not a whole lot, but a little bit. Okay? Good deal. Appreciate your coming. Sorry we missed last week, but they made us go to that meeting. And by the way, it was basically totally worthless. They got something out of it, but we got very little. We did get to interact with others of our peers, and you know that was good, but it was all for their benefit, nothing for our benefit, really. So it was a boondoggle of the highest nature. So sorry that we missed class. All right. All right, we'll catch you then next Wednesday. Last class, and we will do, I'll give you your last test and then. If you finish this one, get it in to me. If not, we'll get it back to me the following week.
Have a good night.
You too. Thank you so much.